CLion, a cross-platform IDE for C and C++. Download now.
Welcome, everyone. This is Deciphering Coroutines, Mastering Asynchronous Control Flow. This is me. You can find me in various places on the web. You can shoot me an email if you want. And as some of you might know, I'm one of the co-organizers of the Munich C++ user group. We are one of the biggest users group in the world. If you ever want to spend some time in Munich, maybe want to give a talk, please reach out. We're always happy to welcome new faces. So this is actually part 2 in a series of talks on coroutines. You can find part 1 from 2 years ago on YouTube. And this talk assumes familiarity with the contents of part 1. If you were in Phil Nash's talk earlier today, he covered pretty much the same ground that this talk did cover. I, of course, used like slightly different conventions for presenting it. I will give a very brief recap in the beginning to refresh in your mind. I won't have time to go into the mechanics in detail again. So if you've never used coroutines at all, then this is probably not a good place to start. If you're watching this on YouTube and you're in that situation, I would advise you to check out this talk or Phil's talk, for example. So let's do a very brief recap of the basics just to make sure we're all on the same page. So a coroutine is basically a function that can be paused in the middle, and then I can resume it later on, and all of the remaining state will still be intact and will just continue executing at the place where I left off before. And if you look at the coroutines language mechanism, there's 3 major parts to the mechanism. The first one is the coroutine return type. That is really the return type of the coroutine function that you're calling. And this is a user-defined type. So when you're writing a coroutine, you as the user, you get to decide what this type looks like. You can either write your own from scratch, or you can use something like the generator from a library. And this type really defines what the interface of the coroutine is going to be like, and it really determines what it is that you can do in the coroutine, because there's lots of different patterns that you can implement with the mechanism. So in C++, the coroutines are pretty flexible. So there's really a wide range of behaviors that you can implement here. And the goal of this talk is to help us understand one particular use case better, and that is going to be the asynchronous I/O. So a simple example for a return type. So the first thing that we notice is if we just look at the signature for a coroutine, since the return type is a custom user-defined type, but just by looking at the signature, you cannot tell whether a function is a coroutine or not, right? From the outside, it looks just like any other function. So the way to think about is when you first call the coroutine, the initial call is really like you're calling a factory function that produces this return type object that you then hold on to. And all of the other things are then things that you do with the return object. And the fact that this is implemented internally in terms of a coroutine, that is almost arbitrary, right? You can implement all of these interfaces also without using coroutines. In some cases, it's very hard to do so, but coroutines don't really make the language more powerful in that sense, right? They just make stuff easier that would be quite complicated to do otherwise. So in C++23, we got a very simple library type that we can use as a return type here, and that is the generator. Phil also explained this morning quite extensively how that works and how you can write it yourself. As a user, what it allows you to do is from the coroutine body, you can yield values. And then what the caller of that coroutine can do is it can iterate over the generator like a range. So it works with all the facilities that accept a range, like the range-based for loop. And then like each new element of the range that we request from the generator is one of the values that is yielded by the coroutine body, right? And between all of the yields, the coroutine body goes to sleep, and then it only resumes later when the user asks for the next value. The second part of the facility is the promise type. So if we think of the return type as the facility that determines the user-facing interface, then the promise is really like the compiler-facing interface. This is what allows us to configure like what happens at certain points during the execution that the user doesn't have direct access to, but that the compiler needs to generate to run the whole mechanism. And this provides a bunch of customization points that allow us to customize the behavior of certain vital stages of the coroutine execution. So this is the overview of all the functions that you have in the promise type. So unlike the return type, which is really like fully custom and you can do whatever you want, for the promise type, the compiler actually tells you what the functions are that it expects to be there, and you still have pretty great freedom in what you write into the body of those functions, but you always need to provide those functions. And you will notice that these are mostly functions that are invoked during the startup and the shutdown of the coroutine. So that's the main behavior that we are customizing here. And the other thing to note here is that the user never calls any of these directly, right? This is an interface between your coroutine and the compiler, like the language mechanism underneath. So that makes this a little bit weird and unlike other standard library interfaces that we have. The third part that we have is the awaitable. And the awaitable is any kind of object that we can use with the operator co-await. And the operator co-await is what triggers the actual suspension. So when the coroutine wants to go to sleep, that's actually when the awaitable comes into place. And because of this, what the awaitable offers are customization points similar to what we find on the promise, but these control the behavior surrounding the suspension. So we can customize what happens before the coroutine goes to sleep and what happens right after it wakes up before you hand the control back to the coroutine body. And again, like with the promise, these are not functions that user code calls directly. This is a compiler-facing interface. Then in my previous talk, I also showed like this little diagram that allows you to visualize a bit better how all of these different parts are connected and how they interact with each other. The important thing to notice is that the promise at the bottom is sort of like a central object that glues together the two worlds, like the caller that calls the coroutine, that is the client of the coroutine and the coroutine body. It's like two different worlds, and whenever they want to exchange any kind of data, they have to go through the promise because that's the thing that sits in the middle. So if you are familiar with part one and you like this diagram and it helps you, here's a QR code that takes you to this. Feel free to use that to follow along. I will leave that on here for a couple of seconds so people can scan it. So why am I back now with a part two? So at the end of my first talk, I said, we now understand all of the boring parts of the language mechanism, and now we can actually start doing interesting things, right? Like part one was just like really language fundamentals, boring machinery, and going through all of these interfaces in detail. So in this second part, I want to focus actually on a real use case and a pretty prominent one that is mentioned quite often, and that is asynchronous computation. So other languages have dedicated features for this. If you look at C#, Python, JavaScript, Rust, and others, they all have this async await mechanism, right? Which under the hood does about the same thing that the C++ coroutines does, but if you are familiar with how it works in those languages and you saw all of the basics, then it's not obvious how that fits together, right? There's a mismatch there. There's like you need to do some manual work in C++ to get to the same kind of powerful feature. And that's the goal of this talk, actually, to close that gap and to give you an idea how you can implement something like async await in those languages with the C++ language coroutine mechanism. So one problem with coroutines is always that there's a lot to explain, and that makes them very challenging for a talk. In this particular case, that means I won't have time to talk very much about motivation for like why this is useful for asynchronous computation in particular. If you want to know more about that, if you're not convinced that this is useful at all in the first place, I recommend Andreas' talk from Code Dive 2023. This is a talk that focuses entirely on the motivation. It does not explain anything of the inner working. It's really just the user view from the outside, and it shows you very clearly like why this is a good thing to have if you're living in an asynchronous world. If you don't like watching talks for this, if you like to see code, what I can also recommend is you go to the Boost ASIO documentation, and they have a section with examples there. And what they do is they start with the same basic example, which is basically an echo client server, right? So a client sends a message to a server, the server sends the echo back. So very simple communication, and they implement this same example with different paradigms. So you can start with the C++ 98 version, you start with the blocking version, then you go to the 98 asynchronous version, and then you can go like through the different language iterations, through the different standards, and you can see how the example changes with each of them. And it's really worth doing this and going through all the different versions. And then once you arrive at the coroutines example in C++20, you will really see that like this is a journey, right? And when you come out at the end, you will understand how it comes full circle and why this is useful. So before we dive in, a few words of caution. I will at times lead you astray here in this talk. This is intentional and will hopefully help to deepen your insight why things are the way that they are, not just present the final image. We will largely be ignoring multi-threading here. That's a whole can of worms of its own. So I'm just going to assume like a single-threaded asynchronous world here. And lastly, this is not a best practice talk. The goal here is to like develop your intuition for what is going on behind the scenes, but like this is all slide code, right? This is not something to copy paste into your library or production code. All right, let's start by building a mental model for what we're doing here. So an easy intuition to start with for coroutines is thinking about cooperative threads. So let's take a really abstract example, right? We want to compute some complex task. It consists of like several functions. We have an outer function that calls a middle function, and that middle function will call an inner function, and this inner function eventually needs to do some I/O, right? And the easiest way to do that is we just have a blocking I/O call, but this of course could now take some time until like the device replies and we can continue. So this entire stack of computation is blocked, right? Everybody, like all the future computation steps rely on that result from that asynchronous I/O, from that blocking I/O operation to be there. So until then, we can't really do anything useful here. So wouldn't it be nice if instead of just waiting and doing nothing, the main thread could just suspend this entire stack that makes up the task, save it somewhere to the side, and do some other useful work in between, right? So that we don't waste precious time doing nothing. So a straightforward solution to this is just use threads, right? So instead of just spawning the task by just calling the function, we call the function on a separate thread. And now what happens is all of these functions, they execute on the side on a separate thread. And the main function retrieves a handle, which could be something like a future, that can be used to retrieve the result once it's available. But while all of these functions are blocked, waiting for the I/O, the main thread can do useful stuff in the meantime. So of course, threads have their problems. So thread creation is pretty CPU and memory intensive. That might be a problem if you want to create a lot of them. Thread switching is also comparatively expensive, right? You need support from the operating system there. There's a pretty heavy context that you need to take into account here. The blocked thread still consumes CPU cycles, right? Even though your main function is able to do other stuff in the meantime, that thread is still there. And depending on how smart your operating system scheduler is, it might still burn through CPU cycles. Also, if you have threading, sharing data becomes a problem. You now need to worry about data races. You need to worry about synchronization, and that is very hard to do. And there's other problems. So in the context of asynchronous computation, really the biggest problem with threads is that they don't scale very well, right? This works reasonably well if you only have like a few tasks up in the air, but if you have like thousands of tasks, right, and they're all waiting most of the time, then this comes with a lot of overhead, and this is not the best solution. So a more lightweight approach to use here is what is sometimes called green threads, or also fibers, or user mode threads, or also stackful coroutines. So how does that work? So instead of spawning a thread, we're spawning a green thread. And now in the function that actually performs the blocking operation, instead of just doing a blocking call, we actually split the operation up. We have a setup phase that actually dispatches the I/O call, and this returns immediately. It's a non-blocking function. And now, while that result is being obtained in the background, the thread actually cooperatively relinquishes control, right? So the thread says on its own, please put me to sleep. I'm just waiting for some result that is not there yet. And then at some point, this thread will get woken up. And then I can just retrieve the data, which is hopefully already there at this point, and continue with the operation. So the crucial difference here to the threading approach is that this is not a preemptive approach. This is a cooperative approach, right? The thread has to voluntarily say, at this point, I cannot continue. I want to suspend. I want to give up my execution thread. So the way that this looks like in the diagram is actually quite similar to what we have with the threading. So the main function spawns up the green thread, which then gets created in the background. And now the main function has to voluntarily give control to that green thread. The green thread will run until it reaches this point where it doesn't want to continue anymore because the result is not available. And at that point, it will call this suspend function, and then control will get handed back to the main function, right? So it's like we have all of these threads up in the air. They can all be referred to by these thread handles. And then through these suspend functions, I can pass control from one green thread to the other. And yeah, so the main function can do other stuff while the green thread is suspended. And then eventually, when the I/O operation completes, main itself suspends and control is handled back to the worker thread. So that's the idea here. So green threads have comparatively little overhead to threads, since I only have one operating system thread, right? And all of the context switching is done in user mode. There's also no synchronization needed because there's no true parallelism here, right? There's only always one thread running, and because all of the context switches happen cooperatively, it's pretty clear what the points are at which my execution will get interrupted. So synchronizing this is like you can't get any data races, and the amount of synchronization that you need when switching from one context to the next is significantly lower. So yeah, the green threads decide cooperatively when to suspend and to resume. But in general, our intuition about control flow is still similar to threads. So if you've already worked with threads and you know how to use them, then green threads it's a very similar model, but it's just easier because a lot of the issues that you get with threads are not there. So what about C++20 coroutines now? So the biggest difference with the C++20 coroutines and similar mechanisms is that they are stackless. And what that means is, well, with the green threads, I can just say, yeah, suspend this task, and then it will suspend automatically all of the functions, like the full call stack that was associated with that operation. With C++20 coroutines, if I suspend a coroutine, I only suspend the one function that I'm in, right? And then control is handled back like one level up the call stack. But if I have a complex task that is made up of multiple functions, that doesn't work out of the box. So what we need is a mechanism that allows us to do that. And that's really the entire point of this talk, exploring how to do that. How we can suspend an execution context that is larger than just a single function. So let's try to get an overview how to do this. So if you are like me and you come from a threading background, and that's your mental model of how to do things, you might come up with a roadmap similar to this. So you want to start by spawning your task, spawning the outermost coroutine. Then you call all of the nested coroutines, and that's trivial, right? That's just function calls. So we don't even need to do anything special here. Then at some point, you want to suspend the entire coroutine stack, like we did with the green threads. Then it goes to sleep, the result arrives in the background, and then you need to resume the entire stack, right? So you wake all of the functions up again, one by one. And then eventually the result becomes available, and you need to deliver the final result back to the different context. So the interesting point here is the question: how do we do this suspension of the entire stack, and how do we wake it up again? Right? That's really the core. If we can do those two things, we know how to do this. So let's start by suspending how we would do this. So we just start with normal functions. If we want to suspend them, we need to turn them into coroutines. How do we do this? Well, we need one of the coroutine keywords in the body, and the return type changes to a coroutine return type, right? So I'm just going to call it async here, for lack of a better word. Some people also like to call this task. In WG21, people were proposing lazy for that mechanism, right? But like this is just our return object for saying, this is an asynchronous function that is part of a bigger asynchronous computation. Right, and this is pretty much it. There's not much more to do at this level, right? We still have to figure out what this return type looks like, but these are all of the changes that we need to make to the individual function. And then, of course, we have to do this also all the levels above that, right? So we have to mark everything as async. And all of the nested async operations, we have to call them using co-await, right? And if you're using await async in other languages, that's exactly what you do, right? So you mark all of your functions as async. And if you call an async function further down, you have to do that through the await operator. So that shouldn't be very surprising. Right. So one thing to note here, if we actually like split up this co-await line, we will see. So what happens here is the inner function, it returns an async IO result, right? That's its return type. And now we co-await on that async IO result that was returned by the inner function. So if we use our little color coding from the beginning, then what we see is this async IO result down here in the function, that's an awaitable, right? So that's the green thing. But in the inner function up there at the top is the return type of that function. But it's the same async IO result object, right? It's just in the different contexts, it plays two different roles. So this is something new. Like if you only saw the generator example that we did in the first talk, you never had something like this, right? In that example, it was always clear each type plays one of the three roles. But now what is new here is that this async object, it plays two roles, right? And that makes it very different from the coroutines that we saw before. Okay, but other than that, in terms of calling the nested coroutines, that's all we need to do, right? We just sprinkle async and await in there, and we're done, right? So how do we now suspend the stack? So that tells us how we suspend the stack. But how do we resume it, right? How do we wake them up? All of these coroutines now went to sleep. Now we want to restore our task. So let's look at what happens when we are suspending these nested tasks, right? So we have these three functions that make up our computation. So main calls the outermost function here. That will then build up this entire stack, and eventually the inner function, it will reach this point where it does not have its result available, so it goes into suspension. Then the inner function disappears off the call stack, hands control to the middle function, then that one suspends as well. Then the outer function also suspends, and then we're back to main, right? At this point, main is free to do other stuff in between. And eventually, main will want to wake up all of those functions again to continue with the task. So at that point, await resume will get called, and then all of the functions will reappear. And then we have restored our full call stack. And then like we did with the green threads, we can now just continue. And none of those functions will see any difference. They resume right in this state where they went to sleep before. Okay, so let's zoom in a level, right? That was just a very high level overview from main. So how would this look like in the outer function? So this function, it calls the middle function, right? The middle function eventually returns. Then we get here to the co-await call, like we need to wait for some results. So this function now goes to sleep. Await suspend is called. The function is paused at this point, right? Now stuff happens in between. Eventually main wakes us up. And now what happens? So main resumes the outer function, right? Since we're resuming from the outside in. So this function continues execution. And what does that mean? Well, co-await returns. Await resume is called. Co-await returns. The outer function continues executing in its body. And wait, the next thing in the body is the result. But the result is computed by the middle function, but we didn't resume the middle function yet. So this doesn't work. So why doesn't this work? What is the problem here? So in general, like what we were trying to do is we were trying to resume coroutines from the outside in. We were coming from this intuition from the green threads, where we were trying to reconstruct the call stack that we had in the beginning. But with stackless coroutines, that does not work. That's not how we do things. And the reason that this doesn't work is once a coroutine has been resumed, the only way that it can go back to sleep is if it calls co-await again on something. But like what would we call co-await on, right? We would have to co-await again on the middle function, right? Because that's what we're waiting for. We're waiting for these inner functions to complete their work. But we don't know how many more times they need to suspend and resume before they have their result available, right? Like in our simple example, there was only a single asynchronous operation, but there could be like 5 or 10 or 100 asynchronous operations. So those inner functions, they need to suspend many, many times before their result is available. So we need a different mental model here, right? Our mental model for co-await should be, if we are co-awaiting an async function, we want to suspend until that function has completed and its final result is available. And we don't want to be woken up in between. So that means that like this inner function will be resumed probably multiple times without the outer function, like the outer function does not want to be bothered, right? The outer function only wants to be woken up once that inner function has finished execution and its result is available. And that's a crucial insight here. Because that's like, if you're coming from this intuition of like cooperative multi-threading, then this is counterintuitive. But that's how you do things with stackless coroutines. And we will see in detail how to do this. So the crucial takeaway is like this easy intuition here, that doesn't work. Our naive roadmap, it was too naive. We need to do something else. So let's step back a bit and think about what is a call stack anyway? Like what is going on, like in the simple synchronous case, what is actually going on when we have such a stack of functions that do a complex computation? So if we look in memory, a stack frame is really, like we have 3 registers and a bunch of memory, and that's the whole state of our function. So we have the base pointer, which is sometimes also called the frame pointer. That's the beginning of our stack frame in memory. And then we have the stack pointer, which points to the end, like the upper or lower portion of the stack. And like everything between these 2 pointers, that's the state of our function, right? That's all of our local variables and objects that we created. And then we have the instruction pointer, and that simply tells us where in the function we are, at which instruction we are currently executing, right? So if we have these things, and we know like this memory region and everything that's in there, and the instruction pointer, that's everything that we need to reconstruct the state of the function at any point during the execution. And now, the way the call stack works is it stores for each stack frame right below the base pointer, the frame pointer and the instruction pointer of the caller of this function. So, and if I have this, right, if I have the frame pointer and the instruction pointer, I can reconstruct the state that my caller was in when it called into this function, right? Because like its frame pointer, its base pointer tells me where its stack frame started in memory. The end of its stack pointer I can just reconstruct because that's just at the bottom. If I pop all of the memory and the frame pointer and the instruction pointer, then that's the stack pointer of my caller function. And the instruction pointer, that's just the instruction that I need to jump back to. All right, so if you look at like how do functions look like in memory, how does function call work on the assembly level, then these are the crucial parts. And the global view of this is that if I start from the base pointer register and I walk through all of these frame pointers, then they form a single list of stack frames in memory. And the list is oriented in that way that we always link from the callee frame to the caller frame, right? So if we now want to do these asynchronous computations with these many operations that form like this call stack, which is now no longer really a call stack in memory, we somehow need to do something like this on our own, right? Because our coroutines so far, they're just isolated objects, right? And once a coroutine suspends, it just hangs up in the air on its own in a suspended state. And we now somehow need to connect them so that we can say, okay, like this other coroutine over here, that's actually my caller, so to speak, in the asynchronous context. That's the one that is waiting for the result that I'm working on right now, that I'm computing. So here's what our roadmap needs to look like. Yeah, we still need to spawn the outermost coroutine. Then we need to call the nested coroutines. And when we suspend the innermost coroutine, and then suspend them one by one as we're going up. But when we resume the innermost coroutine, and we resume only the innermost coroutine. And then only once that innermost coroutine has completed, once it returns or falls off the end, then that resumes the next layer. That resumes its caller, the next outer coroutine. And I go through these layers one by one until I've exhausted the complete asynchronous call stack. And then I have to deliver the final result. So this is probably the most interesting part here, right? How do we do this? How do I resume the outer coroutine from the inner coroutine? So if we think back to the call stack, the reason that this works in like normal function calls is because I have all of this information laid out in memory on the call stack, right? I just need to follow the base pointers, and that gives me all of the information that I need to restore my caller state and hand control over to it. And the reason that this information is there is because it was built when we actually went down the stack, right? When we call the function, then we put all of that info on the stack so that it's there for us to use when we return. So if we want to solve this problem, we really need to think about this problem, because it's not enough now to just call the nested coroutines. We also need to establish at this stage the links from callee to caller. Because if we don't save that information here, there's no connection, right? The coroutines are just floating in the air. So we need to establish that information at this point so that we can use it later. And that's the first thing that we're going to look at now. So I'm introducing a new color coding here. I hope it's easy enough to follow. So from now on, whenever a function is marked in the indigo color, like the inner function at the top, that means that is the inner function. It's the callee in this context. And the caller in such a context is always marked as orange. So the mnemonic here is the inner function is the indigo function, the outer function is the orange function. Hope that makes sense. So as we saw before, the async plays two roles here. And we're going to start by inspecting those two roles in isolation. We're going to start with the role that it plays for the inner function. In the context of the inner function, the async is a return object of that coroutine. So what do we need there? So the return object needs to specify the promise type. And a convention that we saw in part 1, what you usually want to do is you also want the return object to maintain a handle to the coroutine that this return object belongs to. So in this case, that's the handle to the inner function. And the way to do that is you just use the getReturnObject function, which creates the return object that's handed out to the caller. There you have access to the handle by doing this little dance here. And then in the constructor of the async object, you can just save the handle. And then you have it, right? We did this in part 1, and I think Phil also showed it this morning. I'm actually not sure if he showed it. But yeah, this is how you do this. This is very straightforward. You almost always do something like this when writing coroutines, so that shouldn't be too surprising. So, and that's really all that it needs to do from the return object perspective. It needs to save this handle to the inner coroutine. So let's switch gears now and now look at the other side, right? We're now observing this object from the perspective of the outer function, of the caller function, right? So the object, the async object here, that's the thing that falls out of the inner function that we called, and now we co-await on this object. So the role that it has to play is the role of an awaitable. So we need to implement these 3 functions here, like for every awaitable. So await ready, that determines whether we actually want to go to sleep or continue right away. Like in this case, we don't have any reason to continue, right? Like the inner function wanted to be suspended, so its result is not there, right? So we're never ready, we always return false here. Await resume, we don't quite know what to do there yet, right? Like this is the function that determines where to get the result that now the outer function continues computation with, right? This determines what value falls out of the co-await call when it resumes. So yeah, we're not quite sure what to do there yet. But the await suspend, here we notice something interesting, because the thing that the await suspend gets as a parameter is a coroutine handle. But think what this coroutine handle is, right? So await suspend, that's the thing that controls what happens before the coroutine goes to sleep. But which coroutine goes to sleep here? This is the outer function, right? It's the caller function that calls co-await on the async object that was handed out from the inner function. And this handle, that's the handle to the function that wants to go to sleep, the function that called co-await. So this is the handle to the outer function down here. So we have 2 handles here, and they refer to different coroutines. One refers to the inner coroutine, the other refers to the outer coroutine. And that's the connection, right? That's what we need. We need a point where we can establish that, hey, these coroutines, they actually belong to each other. One is the caller, the other is the callee. So that's what we do here. So at this point, we can actually establish that connection. So we save, in this case, I save it straight to the promise. I save this handle as, hey, this is my caller. This is the function that actually needs to be resumed once my result is available and I'm ready to return. And what that means is if I now have a structure that is very similar to what we have with the call stack before. I now have this linked list from caller to callee in the asynchronous context. And that's actually all that we need to do here. So let's take a look now how we can resume stuff now based on this. So we have established all of the links, right? Each function knows what its caller is. And now, how do we actually resume, right? So if we think what is going to happen here, at some point the inner function is going to be woken up. It will have completed all of its computations, and then it will return, right? It will either call co-return, well, if it produces a value, it will probably call co-return, right? And then say, hey, this is my result. So we have this handle to the outer function that we saved in the promise when we went into suspension. And now, where can we use this actually, right? So because if you think about the return value function, where the inner function stores its result, yeah, you could call resume on the handle in there, but then you would have this weird situation that now the inner function calls the outer function, so you would get sort of an inverted call stack. And like the inner function really has no place of being on the call stack anymore because it's done, right? Its final result is already there. So that is awkward. That seems wrong. So what else can we do? Well, the only other place that we have is the final suspend, right? That's the only thing that gets executed after the return value. And the final suspend, the only thing that we can do there is determine, like provide an awaitable that the compiler will call co-await on after my, as the part of finally suspending the inner coroutine. So that thing is sort of the key, right? What we want to do is we want to write an awaitable here that instead of just suspending the inner coroutine, it actually resumes the outer coroutine, the my caller here, right? If we can do that, then that's what we wanted, right? So how can we write such an awaitable? Let's try to do that. And as you will see, it's actually more easy than you might think. So again, await ready and await resume are easy because await ready, like we never want to continue, right? The inner function is gone. We want to go through with the suspension here, so that's always false. It's never ready. Similarly, await resume, like we don't want to be resumed. The inner function is done. It's in the final suspend. All we want to do is hand control over to our caller, but we never want the inner function to wake up again, right? It fell off the body. There's nothing more to execute. So we just leave it empty. This will never be called. You can put a terminate in there if you're feeling paranoid. This should never be called. So the only thing that's left is the await suspend. And if you saw Phil's talk this morning, he was saying there's 3 ways that the await suspend can return, right? It can either return void, in which case you will just go to sleep. It can return a Boolean, which means like depending on the value of the Boolean, you either go to sleep or you continue right away. Or there's this third thing, which is called symmetric transfer, which means you return a handle to another coroutine. And now you, the coroutine that somebody called co-await on, you go to sleep. But instead of returning control to the caller on the normal call stack, you resume that other coroutine. And it continues executing in place, in your place. So that's called symmetric transfer. And since that is a little bit confusing, we will look at that in a bit more detail, what exactly is going on here. So down here we have the call stack, as it would look like in a debugger. So there's like some base function, like whoever resumed the inner function. We don't care about that guy. So we're now in the inner function, and the inner function is done. It wants to return. So we're at the red arrow here, and we want to get to the peel arrow in the corner, right? That's where we want to end up in. We want to resume the caller for that function, which is not on the call stack, right? Since all of the coroutines are just suspended things that are hanging in the air, and they're only connected through these handles in the promises. So what happens is the inner function is done, right? So return value is called, it stores away the data somewhere safe. And then final suspend is called. We get to final suspend, and here we return our magical resume caller awaitable that we wrote earlier. The compiler will call co-await on that. So we will end up in the await suspend function of that resume caller. That will return the handle to the calling coroutine, which we stored away when we initially invoked all of the all of the coroutines for the first time. And here now the interesting thing happens, right? So now, until now, this is just a normal call stack down here. But now what happens with the symmetric transfer is that the inner function goes away and the middle function takes its place, right? So control never goes back down here to the base. It's those two functions, they switch places. And the middle function continues executing in place of the inner function. The inner function is now suspended. And the base has no idea of what was going on, right? Like eventually, if middle function now returned to base, base would not know that control actually was passed there, right? This happens, inner function just pass control over, and they just swap the places here. So what happens now? Like the inner function, it's done, like its body finished executing, but now it hangs in the air in this suspended state. So what happens is that the middle function now, it wakes up, right? Await resume on this awaitable that was returned by the first call to inner function. That resumes now. And then the body of the middle function continues executing, right? So we are now at the red arrow up there in the middle function. And this now moves to the next line. But remember that like in this co-await expression, what really happens is we are co-awaiting on the temporary async object that was returned from the inner function. And now when we move to the next line, that object goes out of scope, right? There was a little async temporary object that was living there inside the co-await expression. And when that gets destroyed, in the destructor, it now calls destroy on the handle for the inner function, right? So here the inner function was still suspended, but it was still there. And now the destructor calls self.destroy, and now it goes away. So it's still cleared up. It's still like you would expect it. The lifetimes are nested. It's just that the order of events is a little bit different because it's only cleared up at this point when the object goes out of scope. And if the middle function does weird stuff, of course, it can keep the object alive indefinitely, but why would you want to do that? So this is an overview again. This is how the resumption mechanism works. And I'll give you a few seconds to take that in. And then once more, since it's so unusual, the call stack, right? The inner function gets resumed on its own. Eventually, will run to completion. Final suspend will get called on its promise. That will return this resume caller. And then the resume caller will initiate the symmetric transfer, and then the inner function will just disappear off the stack. The middle function will take its place, and it will continue executing. So that's how this works. That's how you resume an outer coroutine from an inner one. And that's the most important thing here, right? That's how you can connect different coroutines and form like this asynchronous call stacks, form these complex tasks that are composed of multiple coroutines. But we still have some blanks here, so let's fill them in. So we know now how we can resume from, like, if I'm in a coroutine and I'm done, then I know how to resume my caller on the async call stack. But somebody still has to resume that innermost coroutine, right? So we have that guy there on the very left that is just waiting for this blocking I/O, and somebody has to wake him up. How does that work? So yeah, what we're doing here is we're calling some async I/O function. And I don't really care in detail what that looks like. The crucial part is that whatever that looks like, it will probably not return an async of something, right? it will return a different kind of awaitable. I called it IO awaitable here, right? So that's the awaitable that represents I want to be woken up once that result from that IO operation is there. So this is a different thing. That's a different mechanism here. So the way that this works is if you think about it, I'm requesting an IO operation, right? So then somebody like goes to the kernel and like sets that up, does an async read on a socket or whatever, right? And now I return, this guy goes to sleep. Somebody at some point needs to check whether the operation has completed, right? It needs to do a select or an epoll on that socket or whatever. And then when that facility, whatever that is, recognizes, hey, this result is available, then we need to wake up the inner function. So there's some mechanism needed here that manages these pending IO requests and that wakes up this function, that resumes this function whenever it's time to be resumed. And I'm just going to call that facility the scheduler for the lack of a better word. So for the remainder of this talk, whenever I say scheduler, that's what I mean, is that facility that manages all of these outstanding IO operations. And I will even show you what that could look like, because it's not very complicated. So what the scheduler needs to be able to do, whenever somebody asks the scheduler, hey, like of all the pending IO requests, is any of those ready? Then it will either say, no, none is ready, or it will say, yeah, sure, this handle has an operation that has already completed, right? So that's what getReady does. It either returns null opt if nothing has completed or nothing is there, or if something has completed, I get a handle back to one of the operations that has completed. Then I need a run function that just says, okay, if there is a handle that is ready, please execute whatever operation is associated with it. And then really what this scheduler maintains in terms of data is just a map from handles to coroutine handles, right? So that it can say, like, if some IO operation completed on this handle, then that's the coroutine that needs to be resumed because it was waiting for this IO. Right? And then, yeah, of course, functions, coroutines need to be able to register themselves if they want to do IO, which would just create an entry in this map. And then really, like, all that the run function does is it checks, hey, is something ready? And for all the things that are ready, I just look at what are the coroutine handles associated, what are the coroutine handles waiting for this IO operation that completed, and it just resumes them, right? And it should probably also remove those from the map. Because right now it will just, well, let's assume getReady does that. Yeah. GetReady, yeah, that's how it's supposed to work. So getReady will only return, like, once getReady returns you an IO handle, it will remove it from the map, right? So getReady will never return you the same handle twice, right? Everybody has a rough understanding. Does this make sense? It shouldn't be complicated. Like, if it looks too simple, it's because it's really that simple, right? All of the difficult stuff is whatever the operating system does with the IO underneath. But to handle the request, that's all you need. It's not complicated. And that actually tells you everything about that, right? So suspending the innermost coroutine just means you register yourself with the scheduler. And resuming just means like somebody's pumping the scheduler for all the stuff that has been completed, and then it just wakes you up. And that's all that's happening there. So there is one interesting question here, and that's where does the scheduler come from? Because like where the scheduler typically lives, like the scheduler does not live in your like asynchronous task, right? If you think of this asynchronous call stack of nested functions that make up a task, the scheduler is not part of that. The scheduler lives outside of that, like on the level of main, right? Because like when you're waiting for the I/O, all of those functions go into suspension. So somebody outside of that task needs to tell the scheduler, hey, run, like wake up all the functions that are ready now. So like in terms of simple intuition, the scheduler lives at the level of main, right? It lives outside of our computation, which means we need to pass it in to all the functions that want to do asynchronous I/O. So a consequence of this is probably all of our functions will now need a scheduler parameter. And that's not nice. I don't need to do that in JavaScript. Why do I need to pass the scheduler? Wouldn't it be nice if I could just go wait and it would just know what the, I told him what the scheduler was down there when I spawned the task. Well, why do I need to say it again in every function? So how about this? Instead of just spawning the coroutine, that's the place where I register the scheduler. And now instead of just propagating the links from caller to callee, I also want to propagate the scheduler, or just really any execution context, anything that's related to these operations, so that all of the inner functions have the stuff and I don't need to manually pass that down. This is not strictly necessary. This is more of a convenience thing, but it's really nice. So we're going to look at this. And it will actually lead us to some interesting problems along the way that we've been ignoring so far. So yeah, propagating data from the outside in. Like we had this await suspend function down here on the bottom where we established the links from each function to its caller. So if my caller already knows about some context, I can just propagate that context along, right? Because I'm establishing links here between the elements, so any data that is already available on the outer layer, I can just propagate that down. So that's what I'm doing. I'm just passing the pointer to the scheduler along. And again, here's the color coding. So the outer function, that's the handle that's passed as an argument, and the inner function, that's the handle that I saved away at construction time. So one thing to notice here is the coroutine handle is templated on the promise type. But unless all of my functions have the same signature, the promise type of the inner function is not going to be the same as the promise type of the outer function, right? Because the return object is templated on the return type. If the inner function returns IO result and the outer function returns outer result, then these promises are different. So the promise type here, the one in red, that's a different promise type. So I need a template here. But it also can be any promise type because I expect it to have a field myScheduler, which contains the information that I want to propagate. So I expect all of the promises that are part of such an asynchronous computation to follow some concept. But that's really it. That solves this, right? I can just propagate whatever I want now through the same mechanism. The await suspend is the key here. The await suspend of the async object, that's where I establish the connection. That's where the data flows through. Or is it? So let's look in more detail. So when do we need the scheduler here, right? So the scheduler, that's the thing that I need to register the I/O operation on when I do this async I/O call, right? So inside the implementation of this async I/O, whatever that does, at some point it will need access to the scheduler. So let's look at the order of events during startup here. So we have the middle function calling the inner function. And this is just a normal function call, right? Like we're spawning up our stuff in the beginning. And what happens here is when the inner function starts for the first time, it constructs its promise, right? That's part of the startup of the coroutine. But at that point, when the promise constructor is called, it does not know the scheduler yet, right? There's no arguments there that would tell us this, so it can only set it to null, right? It doesn't have the scheduler yet. So now what happens is the inner function starts executing, eventually it gets to the async I/O, and now it wants to suspend. But before it can suspend, it has to register itself that it started this I/O operation. So it needs to register itself with the scheduler, which has not been initialized yet. Because the point where the scheduler gets initialized is out here. Once the inner function resumes for the first time, and the call stack unwinds and goes back to the middle function, now the middle function co-awaits on the return object of that inner function, and that's the point where the propagation happens, right? It happens inside the await suspend of the async that was returned by the inner function. So it happens too late. The order is wrong here, right? This would have needed to happen before I started executing the body of the inner function. So we need to fix this. How do we fix this? Well, we don't want the body of the function to start executing before the scheduler is there or before the execution context has been established. So we say initial suspend always, right? We don't start. Like, all the inner function does is it creates the async I/O object, but then it returns right away. It does not start executing the body. So now let's look at the functions here. What is going to happen? So we start down here in the middle function. It calls co-await inner function, and then the inner function it creates the return object, creates this async I/O result, and then it suspends right away, initial suspend. And control is returned to the middle function. And now the middle function also co-awaits, so it also goes to sleep. So all is good, right? Because when the middle function does the co-await, the scheduler is saved, is propagated, so it's all good. But wait, no, it's not good. Like the inner function didn't do anything, right? Like we never started the async I/O. Everything just goes to sleep right away. This is not useful, right? Like the inner function needs to do something. It needs to get at least to this line, because that's the point where it makes sense to go to sleep, because I'm missing data now before I can continue. But if I just go to sleep right away, that's also not good. So how does this work? So on the one hand, I want to set the execution context before I start executing the coroutine body. But once I've done that, I want to resume the inner coroutine. I actually want it to continue execution so that it can do useful work. So we saw how to do the first thing, right? If I suspend always, control goes back to the middle function. The middle function calls co-await, and that propagates the context down. But now I still need to do the second thing. I still need to resume the inner coroutine. And this is actually easier than you might think, because we can use symmetric transfer here. So remember, the middle function calls await suspend here as part of this co-await. Like it will co-await the return value from the inner function. And the await suspend currently does nothing more than propagating the state here, but it can, right? In particular, like it has all the handles, right? It has access to, it knows what the outer function and what the inner function is. So whatever it wants to resume, it can resume. Because remember, await suspend has 3 means of returning. It can return void, it can return bool, or it can return a handle to a coroutine that we want to resume. And what's the handle that we want to resume here? Is the inner function, right? We want the inner function to complete. So it's the indigo handle, so it's self. So let's walk through this dance, since it's weird, but it actually makes sense. Like, so this is what we want to do. We are in the middle function, right? We call inner function for the first time. Inner function constructs the return object, runs into the initial suspend, and before it gets to the body of the inner function, it suspends. Return control goes right back to the middle function. Now the middle function is here, like between the co-await and the inner function, right? Inner function returned, I got the async IO result back, and now I co-await on this. So I go into await suspend for that async IO result. And now the middle function goes to sleep. But because of the symmetric transfer, the inner function takes its place, right? So that's what happens here. The await suspend returns the handle to the inner function, and now, as we had before, the 2 switch places, and now the inner function continues executing. But notice that the middle function is gone from the call stack. So if you look at it, if you break in the debugger at this point, you don't have the call stack anymore, right? You only see the inner function. And that's this little dance that you do here, right? Where like first the inner suspends, then the outer suspends, and then they switch places. And it seems weird in the beginning, but that's the price that you pay for being able to propagate this data along. And inner function can always rely, as soon as it enters its body, that all of the data is there. So, as I said, this is not strictly necessary. This is a little bit of an extension, but it's a very useful one. So I think it's worth that you saw it once. In particular, if you see this in library code, that somebody does something like this, it's just very weird if you don't know why they're doing this. And yeah, it's a useful pattern. And also then, if you're wondering why in the debugger, none of the functions show up, you always only see one layer, then they're probably doing something like this. All right. We're almost done. Spawning the outermost coroutine. That shouldn't be too hard, right? So what do we have here? Like, at some point, there will be an outer function. And that will return also an async, like all of the functions further down. But now we are in main. And main is not a coroutine. How do we get to the result that is wrapped in that async? So what is the interface of async? What are its expectations to the outer world? So the async, it always starts suspended, right? If I don't do anything with the async, if I just take the object, I don't co-await on it, it will not do anything, right? It's lazy. Just calling the function does almost nothing. It expects the execution context to be set before executing the body, which happened as part of the outer function co-await in the nested case. And then it expects the handle to an outer coroutine to transfer to after completing. That's the minimum amount of context that I need to set. If I don't give it that, then yeah, I can resume the coroutine, but once it's finished, it cannot do its final suspend, where it's supposed to transfer control to like some calling coroutine. And it wants to be initially resumed via symmetric transfer, right? That's its interface. That's how it acts when it's part of the chain. So whatever we do on the fringes would be nice if it could respect that interface. I can also do it differently if I want, right? I can always call explicitly resume or something, but I mean, if it works with that interface, that's sort of the best, right? So let's see if we can make it work with that interface. So we have this task somewhere, right? Which is, I mean, it falls out of the outer function, but really it's the terminating part of the list, right? So it's the whole async task, right? Is part of that handle conceptually. And we have this scheduler, right? Which all of the inner functions that are part of this task might need access to because they want to do async IO or whatnot. So those two things go into a spawn task function, and then what I want to fall out of that function is the final result that was computed by that task. Okay, so what you will probably have realized by now is that spawn task function will have to be a coroutine, right? Because the interface of the async object, like all of the things that you want to do with it, you need to call co-await on it at some point, and you can only call co-await if you're a coroutine, right? As soon as you write co-await in the body of a function, that function is a coroutine. So this return object from the spawn task function, that's a coroutine return object. But as we saw in the very beginning, the caller of spawn task does not know that it's a coroutine, right? So main does not know anything about coroutines. Spawn task, that's the terminal point, right? Spawn task itself is a coroutine, but whatever interface return object exposes to main, we don't want that to include any coroutine-y stuff, right? So what does spawn task need to do? There's two things that the async object expects. It wants the execution context to be set up, and in our case, that was just a pointer to a scheduler. So we just set the scheduler somehow. I used the member function here. You might want to do something more elegant in your code. Doesn't matter. Like, we just want to get that data in there. We saw in the first part how you can get data into a coroutine. There's patterns for that. So that takes care of that. And then to propagate that context down, in particular to propagate the handle that the inner coroutine will resume when it's completed, I need to call co-await on it. And that's really the only things that I need to do to resume it, to spawn it. So let's look at this return object. It's pretty boring, actually, because it doesn't have to do anything. So yeah, it's just suspend never initially, suspend always on final. And yeah, we didn't think yet about how to get the return value back to main, so that's all empty. So this is really the world's stupidest coroutine return object. And nothing more is needed there, because in the end, the main thing that we wanted to do is to be able to call co-await. And we don't need more than this to allow that. So yeah, this is it. This is all we need to spawn. Now the only thing that's left is obtaining the result. So, and this is really like, this is the diagram from part one, right? Like, how do you get data in out of a coroutine? Well, you go through the promise, right? And these are the paths that lead to the promise. So what do we do here? Well, the result of the co-await expression, that will be whatever result was wrapped in the async object returned by the inner function. So at that point, spawn task has the data, and now it just needs to store it in its promise so that main can get to it. And well, the easiest way to it is just use co-return. And then in the implementation of Coroutine, you can store it in the promise. And then down here, okay, like the return object is now templated on the result value. Down here, you just need a member function that allows you to get to that, right? So here in the promise for that templated return object, we added a field v, which stores the data. And then the return value function just moves the data in there in that field. And now we add a member function on the return object interface, which just returns that result back out. So the main function now, it gets this return object, and it just calls result. And then that's it. That's how you get the data out. And yeah, you need to pump the scheduler, of course, in between, because if the inner function was waiting for some I/O result, right, somebody needs to wake that up. So that's what this loop on the second to last line is doing. But like really, this is if you understood what was going on in part one, then this is completely straightforward. This is probably the simplest part here. These outer 2 points, and that takes care of that. All right, so that pretty much gets us there, right? Like that allows us to do everything that we wanted, and even a little bit more with this propagation of the state. But like taking into account what we did there and what we learned about how coroutines interact and the data structure that they form, maybe like we can take this even one step further. So what about saying all of my promises inherit from a common base? Because that's how we propagate the data here. That's like this concept that all of the promises need to fulfill. And in this promise, I can put additional stuff if I want. So let's say instead of just saving a pointer to the caller, I could also save a pointer to the child, right? So I can get like a bidirectional call stack here. So that's how that might look like. And I can establish a doubly linked list here. Before I had a singly linked list, now it's a doubly linked list. And like really, you can put anything you want in there, right? Like any kind of information that you want to propagate, you can put it in there, right? There's no limit. You define this type, go nuts. So if we think about this now, if you have this doubly linked list that allows you to get from any async object in the async call stack to any other, you can now write a function like this that allows you to propagate arbitrary data from any point in the async call stack to any other point. Oh, sorry, the slides got messed up there. So really what is happening here is like what in the synchronous world was our call stack, this magical, inaccessible thing that the compiler constructs in the background and that you really don't get to touch or even look at. In the async world with coroutines is just another data structure. And to hammer that point home, little example. So remember how, like one of the weird things when spawning the coroutines up was that we lose the call stack, right? Because all of the, like when I do these nested function calls, I do this little dance where the inner function suspends, then the outer function suspends, then I symmetrically transfer, and the outer function is gone. So if I put a breakpoint in the inner function and I look at the call stack in the debugger, I have no idea what the context is, right? Because all I see is the inner function and then, yeah, some machinery, and then I'm right in main, right? So this is like if you're used to debugging async code, this is a big problem, right? You also get that in async code that is not using coroutines, that it's sometimes really hard to understand the context in which an operation is happening, because it's not on the call stack, right? It's hidden away somewhere in the machinery. But the call stack is there, right? Like we save the async call stack, it's our little data structure. So how about I don't use the call stack window, I use the data visualizer window. And like I did this with like 15 lines of NetVis Visual Studio code. You can find it all at the Godbold link. And here's my call stack. It's there, right? It's just a linked list. I just traverse it and print it in the debugger. And you can do the same thing in GDB. Like this is not magic. This is just a visualizer for a data structure. So if you think about this now, you're not limited to doing stuff that you can do with a call stack, right? You can do, it's a data structure, right? You can, if you want to resume a function that is higher up the call stack, do like, I don't know, like an exception style control flow where you jump to any point further up the call stack. Yeah, sure, you can do that. Just traverse and resume whoever you want to, right? You can splice two call stacks together if you want. Nobody's stopping. It's just a linked list. Go nuts. If you want to expose a range interface so that you can use range algorithms to iterate over your call stack, yeah, sure. I'm not saying it's a good idea, but if you have a use case, you can do it. So the only limitation here, it's still a structure of linearly nested tasks, right? That's the only constraint that although, what if we just do one more thing? So now it's a tree. And now it's a directed graph. That's all I have. I want to thank Louis Baker and Matthias Spusch, who gave very valuable feedback and discussed this with me. It's, as you have experienced, it's not easy to wrap your head around this stuff, but I hope I could give at least some insights and yeah, you took something away from this. That's it. I'm happy to take questions. Thank you very much.